Okay, so in this video, we're going to continue where we left off last day, and that is in the Morse theorem. So last day, we spoke a little bit about the Morse theorem. We went through the proof of the Morse theorem, and we used induction. Okay, so this is what we did last day. We explained some of this, and then we reached here to some applications of the Morse theorem. So this is where we're gonna begin the video. Yep. Okay. So we have a question here, this exercise. But before we do this exercise, which seems a little bit tricky, let's look at this example. It says to find all the values for which the cube root of 1. So this is one way that this question could be asked, right? To find the values for which and we have this in this form. It could also be stated in words, right? So find all the values for which the cube root of 1, and we could have it stated in another way. So we have 1 here is equal to 1 plus 0i, right? Because we have no imaginary part. So in this form, it's equal to cos of, well, 0 plus I sine 0, because this part here is 0. So now we use our formula from the Morse previously, right? From here, with this n here. So in this form, it's a third, right? Because it's the cube root here. So it's 1 to the power of a third, which is equal to cos of whatever the angle is here. So it's in 0 here, plus 2k pi on this power here, n, which is 3 here, plus I sine, same thing, 0 plus 2k pi upon n is 3 for k, and we begin here at 0. We put 0, 1, 2. So we need to find 1, 2, 3 roots because it's 3. So when k is equal to 0 here, what happens? So let's write this. So when k is equal to 0 here, we have 2 by 0 by 0. This is 0. So we get the cos of 0, which is 1, because all of this here will go to 0, because the sine of 0 is 0. So we end up with, when k is equal to 0, we have 1. Similarly, when k is equal to 1, substitute 1 here. So 2 by 1 is 1. We get 2 pi upon 3 plus 0. And then we find the cos of that. We get negative a half plus, and do the same thing here, root 3 on 2i. Do the same thing for when k equals to 2. We get negative 1 half minus here, root 3 upon 2i. So these are the only roots that we need to find, because we only need to find the first 3 because it's the cube roots and we started with 0. And then we take those roots here and we plug them on our diagram here. We don't need to do it exactly. We just give some average value. So this point here is this, and this one here, this one here. Okay, so we see now that these two roots here, what we got using the Morse theorem, are the complex conjugates of each other, right? So if this x-axis here, or the real axis here, was our mirror line, then this root here would just be the negative of it, which is over here, right? The conjugate. Remember, for the conjugate, we're not concerned with this negative sign that's in front of the half here. For the conjugate, we only change this sign here, which is where we have a plus here and we have a minus here, a negative sign. Okay, so not this sign here, just remember that, right? And of course, we have our first value here, which is 1, which is somewhere about here. Okay, so now that we have done this example, you can try this one here, which is z to the power 3 is equal to 1 upon root 2 negative 1 plus I In fact, let's try it ourselves. Let's pull up my notebook here and let's do it. That's my pen. Okay, let's try it. So we want to find, what was it? Z, Z to the power of 3 is equal to 1 upon square root of 2, then negative 1 plus I. Okay, so this is much more difficult than the last question. So the last question, let's just go back for it for a second. This was asking me for Z cubed is equal to 1. That was this one here. Now I have Z cubed is equal to 1 upon square root 2 negative 1 plus I. So this one is a much more complicated question, right? Not so complicated. Let's see how we could break this down a bit to make it a little bit more simple. So before we even begin, right, let's go step by step. We need to find what R is, and we need to find what theta is, right? So in our previous example, let's go back. We had R, where was it? R was this here, 1 to the power of a third, which is 1, okay? And now we need to find theta, right? Which is a little bit different here. You see, over here, we had a nice number like 1, right? On our Argand diagram. Now we have 1 upon root 2 into negative 1 plus I, which is a little bit more difficult to plot, right? So let's try and plot that and see what we can get. So there's my, okay, great. So we need to find R. Now R will be the same as before because again, it's just 3, right? It's a cube root here. So R will be the same thing. So let's expand this first. So take this here, just to make my working a bit easier. This, I'm just going to multiply inside here, right? I'm going to put this as negative 1 upon square root 2 plus 1 upon root 2 I. You could leave it like this and solve. I'm just going to expand it here to make it a little bit easier for me, right? So that's the same thing as we want to find the cube root of 1 upon root 2 I. Same thing, right? The reason why I didn't was that is we need to find the cube root here, right? So what is one of the first things to do? I'm going to find and convert this to polar form, right? So let's not skip any steps here. So let's convert, let's call it some, what can we call it? Call this star 1, right? Come back here now, we could say converting star 1 into polar form is that how do we convert to polar form? We need to find the modulus. How do we find the modulus? To find z cubed. This is the same thing as the square root, and this is why I multiplied inside here. So that I can get these separately and I can put it inside here. So that is negative 1 upon root 2 squared plus 1 upon 2 squared, which is the same thing as a half plus a half. Of course, all square rooted, right? A half and a half is 1. So the square root of 1 is 1. So this is what we have. Oh, by the way, how do these 2 points here look on my diagram? Let's see if we can look at it visually. So we have positive root 2, which is somewhere here. And we also have negative root 2i, right? So this is the imaginary part. So let's say it's somewhere, I don't know, here, right? So, of course, this is the real axis, my axis. So this is my angle here. Okay, somewhere, let's say here, this point. So theta is here. So I really need to find this here, this angle here. This is my important angle. So what do I need to do now? I need to find the argument, which is, how do we find argument again? The argument is equal to tan inverse of y upon x, which is 1 upon root 2 here. We have 1 upon root all over negative 1, 2, which is the same thing as tan inverse of negative 1. What's the tan inverse of negative 1? It is negative pi upon 4. But when we drew our diagram here, right, and this is my angle here, I'm in quadrant number 2 here. What do I do from my notes? Let's go back to our notes. Okay, where's my notes? Remember when we were speaking about quadrants? Please don't forget this one. Aha. Remember these rules here of quadrants? So we're going to use that from page 13 over here. And we need to find the principal argument, right? So the principal angle, so to speak, right? So let me write it in words here. We need to adjust the angle in second quadrant. That's what we need to do. So how do we do that? Okay, so in order to do that, we need to find okay, so let's write it in with principal angle. I use a symbol here. What did I use? Alpha. Principal angle alpha. You can call it whatever you want. Just using alpha is tan inverse of 1, which is pi upon 4. So therefore, big A. Remember we said we want for principal argument, we want big A. So that we can tell the difference between what is the regular argument when we find tan inverse and what is the principal argument, which is big A, which is pi minus pi upon 4. Pi minus pi upon 4, please. This is easy algebra. It's just 3 pi upon 4. Is this within our range, which we previously discussed? Let's go back to our notes again. What did we say that we need our angle between? Aha, look, it's here. On page number 12, we said that our principal argument must lie between the negative pi and pi. So let's go back here now. Does this lie between that? So this lies within negative pi. Oops, sorry. Theta pi. So after all this hard work, let's write our answer now in polar form, which is r cis theta. Let's write it. R cos theta plus I sine theta. What's r? 1. What's theta? Cos of 3 pi upon 4. plus I sine 3 pi upon. Finally, we're done. Well, not quite. We still need to apply the Morse theorem to this, right? So we need to find actually, let's, for the De Morse part, let's change our color. Let's use green. So we can tell the difference. So all of that before in red was finding out the polar form, finding modulus and argument. Now we're going to write it as the cos of 3 pi upon 4 plus I sine 3 pi upon 4, of course, to the power of 1/3. Because remember, it's a third here, right? It's a cube root. So that's the same thing as if we use the Morse theorem, we get cos of pi upon 4 plus I sine pi upon 4 right here in brackets by using the Morse theorem. So I'll just write DMT. Okay. Now, what's the cos of pi upon 4 here? The cos of pi upon 4 is root 2 upon 2 plus, same thing here for sine, but we have an I in front, right? Root 2 upon 2. So, what do we know about these here now? We know that the argument here, when we found out our principal argument was 3 pi upon 4. So, in our original, let's go back to our original theorem somewhere. Okay, let me prove my induction here. I mentioned this briefly in class. What does K represent here in our De Morse theorem? K tells me how many times the angle, or not the angle itself, but rather when we find our different angles using K equal to 1, sorry, 0, 1, 2, and so on, depending on how many powers we have, right? So previously we had 3 here, right? So we have 3 points. So K measures how many times we go around this circle here, right? So for our question here now, we could say that, let's write it in, so we'll know. So we know that, what do we know previously? Let's just write it back. The argument of z cubed is equal to pi upon 4 plus, right? Just like before, what do we have over here? 2k pi, right? So that is standard plus 2k pi. Obviously, right, k is here. And since, right, and since k does the amount of time that we go around a circle, then we can write that. What can we write? We take in now this here going on here. And okay. Anyways, we can write that this here, our z, where is it? Oh, sorry, it's here. This. We can write this in the form of cos of z is equal to cis theta. So we can write that z is equal to cos pi upon 4 plus 2. Oops, sorry. 3 pi upon 4, our principal argument, plus 2 pi plus I sine pi upon 4 plus 2 pi. Of course, to the power of a third, right? So now I need to bring this third inside here. And to do that, we'll just write it as cos of pi upon 4 plus 2k pi upon 3 plus I sine pi upon 4 plus 2k pi upon, right? And of course, k is an integer. So finally, right, we have to solve this for k is equal to 0, 1, 2, and so on. We can stop at 2, right? So z now is equal to, oh, sorry, I've written it like how we did in the example on the, we could say when k is equal to 0, z0 is equal to the cos of what? 2k pi by 0, but that'll just come up. So I'll just remember it pi upon 4 plus I sine pi upon 4. Hey, this is what we had originally, right? So this is what my original answer was. So let's say if we're not counting this, then let's look at z1. So that's when 1, we get the cos of pi upon 1 here. So we get 2 pi upon 3 plus pi upon 4. That will give me pi 11 pi upon 12 plus I sine 11 pi upon 12. When k is equal to 2, we have z2, which is the, I'm just gonna write in the form of cis now because this is taking up too much space. Because the roots will be the same, right? Put 2 inside here. 2 2s are 4. 4 pi upon 3 plus pi upon 4. That'll give me cis 19 pi upon 12. And let's do one more. Since this was the original answer, let's see what k is equal to 3 is. That's 3. This 9 upon 4 pi. All right, which is the same thing as if you want to write it like this, plus I 2 upon 2. So we see something here now. This looks very familiar. This is my original answer, which means that at the point that k equals to 3, my roots begin to repeat, right? And this is the point at where I stop. So if we were asked, well, how many roots are there for this? So how many roots are there for this question here, in which we have, where's my answer? I had it in the form of, when I wrote it in this form here at the beginning. When I wrote it in this form here, right? How many roots are there for this? We could say, hence, there exists 3 roots for, I'm gonna write it back. Negative 1 upon root 2 plus I 1 upon root 2 cube root of it. right? So this is how we would go about doing this, right? I did the extra root here to show that the roots will begin to repeat at some point in time. So when we have these sort of complicated, not so complicated, but just roots that look like this, right, of this form of z, we see that the working is a little bit more tedious. The process is exactly the same, okay? It's not as easy when we have nice numbers like 1 here, right? So if we look at this exercise here, to solve a z to the power of 5 is equal to 1, we proceed exactly like we did here. The only difference is that instead of 3, we have 5, right? So we're already finding the fifth roots of this, right? So another way could be like find the fifth roots of this and plot the roots on an Argand diagram. Okay, so that could be another way that the question could be asked. So can we do this? Let's try. Let's draw a line here. Let's use a different color. All right, let's look at that z to the power of 5. So my work in here is going to be a little bit shorter, right? So I already want to find the fifth roots. So I'm ready, remain to find the fifth. Let's write in with fifth roots of 1, right? So I'm just going to go through the procedure of this without actually going into the question. So what do we know? I know that I have 1, right? Which is the same thing as my 0 plus 0i, right? Which is the same thing as the cos of 0 plus I sine 0. Oh, 0, 0, not theta. 0. So what do I need to find now? I need to find z is equal to 1 upon fifth of the cos of 0 plus 2k pi upon 5 instead of 3. And the same as this here, right? 0 plus 2k pi upon 5, right? I don't have the space to write it here. In this case, we're going from k is equal to what? 0 all the way down to 4, right? Because 0 will be counted as the first root. So because it's 1 again, right? I already know my r is 1 and so on, right? So instead of going through all that, let's write my first root is going to be what? Again, cos of 0, which is 1. So the first root is 1. That's when k is equal to 0. Now here's where we get interesting. When k is equal to 1, what is z1? It is the cos. So you're going to get the roots here. It'll be the cos of 1, 2 pi upon 5 plus nothing, plus I sine this. So we'll get 2 pi upon 5 plus I sine pi upon 5, right? So do the same thing now for the rest, right? So I didn't need to go and find all that before, because I already did any other question, right? But if we were doing this question, we would have to go ahead and find r, just like I did previously with all that working, and find theta, find the principal argument, and so on. But because it's the number 1 again, I don't need to rewrite it, right? So z2 is equal to cis. So putting 2 here now, we get 2 2s are 4, so we get 4 pi upon 5. I'm just doing it because I want to draw the roots and show you how it looks, right? Then we have cis 3 cis of 6 pi upon 5, because remember, I just keep multiplying, right? Because I have 0 in front. 4 cis pi upon 5. Okay. And if I were to find k equal to 5 here, this is where my roots repeat. Okay, so all that, let's draw the Argand diagram, which is very important. So the first one, obviously, is Z0, that is 1. What about Z1? That was what? Let's go back up. Z1 was 2 pi upon 5. Okay, 2 pi upon 5, maybe it's somewhere here. Pi upon 5, let's call it Z1. Then Z2 was 4 pi upon 5. So let's go here. So this is Z2. Then we have Z3, which we expect to be here, and Z4. So we could connect them like this. Get a nice looking shape here. Of course, my diagram is not to scale, right? But you get the idea of what I'm getting at here in the shape. So this is what I would expect from you when you have to draw your diagram, right? Of course, it'll be drawn much better than this, right? But not to scale and stuff like that. This is just fine, right? So because this one here, the roots were nice and just 3, we drew this. Of course, if the roots look differently, then we will be able to draw it just like I did in my crappy diagram. So knowing this now, example 9 and its solution is already done for you. We did just like before. We went and we found our R. We found theta. Theta, as z lies on the positive part of the x-axis, right? So we take our pi upon 2. So z to the power of k, I made a mistake here. What did I make? I didn't put z to the power of k. Sorry, z subscript k is equal to this. It's a good thing I saw it here, so I can make that correction. So zk is equal to 1 to the power of a fifth, right? So I wrote it here properly. Good. Z subscript k is the nth root of r, right? Cos of all of this, all the way down to n minus 1, right? So how many roots do we have here? The fourth root. So we'll put 0, 1, 2, 3. At 4, we would expect it to repeat. So we take our cos of pi upon 2. When it is equal to 0, we get cos of pi upon 8 plus I sine pi upon 8. When it's equal to 1, we get this. 2, we get this. And 3, we get. And if we want, we can plot and look at these diagrams accordingly. Okay, so for your reading, look at example number 9. The process is exactly the same, right? So you have many examples to work with here. So this takes us to theorem number 3, which is the roots of the equation over here that satisfy these following properties. So we have this first root omega, right? We're just calling it omega, okay? Is equal to cos pi upon 2 pi upon n plus I sine 2 pi upon n. That is a root. So this theorem here is just explaining what we did here in our example. This is what we did. We get this as a root. Any omega to the power of k, where k is an integer, is also a root. The n distinct roots are 1, omega, omega squared, and so on, omega to the power of n minus 1. Okay, that's great. We did something like that here. The only thing that we didn't look at is the sum of the roots, which we will, and the roots form, the sum of the roots here is not difficult to see. We just take these roots here and we add them up, right? And this theorem is telling me here that when I sum the roots, I get 0. Now, this is only, now be careful, when z to the power of n is equal to 1. The sum of the roots is 0, right? So this is a nice result to know. So that if we get another question, so we just did z to the power of 5 is equal to 1. We did z to the power of 3 is equal to 1. So if we have any other form like z to the power of 6, then we know that the sum of the roots is 0. So that when you add your roots, you expect to get 0. If you do not get 0, then you know one of your roots or some of your roots may be incorrect, right? So this is a nice way to check. The roots form the vertices of a regular n-gon. That is this diagram here. It's not really drawn to scale, right? But it's an n-gon, right? It's supposed to look a little bit skewed. So this takes us to theorem number 4, which tells us that let n be an integer and let z be equal just as before. Then 2 cos n theta is equal to this, and 2I sine n theta is equal to this. So we have a small proof here of this theorem. While that is important and very short, what we need to do is be able to use this to solve some interesting questions. So we can just briefly look at the proof here. We use the Morse theorem here in order to show that we have cos n theta plus I sine n theta is equal to this, just as before. Now you're probably seeing capital or big N, sorry, big Z here to the power of n, right? I just use this distinction here as opposed to the small z or z as before, in order to just create a distinction between what we did before in terms of using the Morse theorem to solve these types of questions and using this result here, right, in order to do something that is a little bit different, right, and which involves using the binomial theorem, right? So that is the only reason why I use big Z over here, right? Not that this Z is some crazy different Z from before, right? So we know that cos n theta minus I sine n theta is equal to this. So we have this here. So if we were to go ahead and add them, then we'll get 2 cos n theta. And when we have the subtraction, we get this. I'm interested in using these inside my questions that is to come, right? So before we apply this theorem, let's remember what the binomial theorem was, right? So I included the binomial theorem here because I know that many of you may have forgotten this from CAPE, right? So we have it here. So this is what the binomial theorem is. So let's look at this exercise here, right? I already did the solution here. It says to prove that this 8 cos to the power of 4 theta is equal to all of this. So I have to use the binomial theorem here, somehow be able to break it down, identify when I get to this form, so I can just substitute either 2 cos n theta or 2I sine n theta to be able to get this result here, right? So I take the left-hand side here and I put it in this form, 1 upon 2 z plus 1 upon z to the power of 4, right? So I factorize here in order to get 2 cos theta because I know already that 2 cos n theta is equal to this. So that I can get this in this form and then apply the binomial theorem, right? So that's what I did here. So we're using the binomial theorem before. It's the largest power we start with, and then subsequently we just keep minusing 1 from the powers, right, until we have none here. And then we, of course, use our n choose r formula. We break it down, we get this, right? So this from here to here should be very simple. Then I look for which of my forms here resemble this now. So we have to learn these, right? Learn them, remember them, commit them to memory. When I do that, I will see that I get my right-hand side. So it's just an application here of using the binomial theorem to be able to solve questions like these, right? Let's look at the second one. Sine to the power of 5 theta in terms of sine and cos of multiple angles of theta. So I'm doing the same thing again, right? So, but this time I only have sine. So this one was an example involving cos. I gave you the answer, so you work towards it. This time is like sine to the power of 5 theta, but I don't tell you what this side looks like, so you have to solve it now. So the procedure is exactly the same. I put this to resemble this form here. And that's what I have here. So 2 to the power of 5, I to the power of 5 sine to the power of 5 theta. But we already know what 2I sine n theta is, which is of this form, and n is 5 here. Use the binomial theorem and substitute your values. Break it down and look for the ones that resemble, this form here. which is these here, right? So when I do that, I see that I have 2i sine 5 theta, I have 10i sine 3 theta, and I have 20i sine theta here, right? I divide over here by 32 in order to get this here, right? We can also express cosine sine exponentially, and we could probably do this in our next class, right? So just review this, and I leave part 3. Maybe we can put it on the next assignment for you guys to try, right? It's just substituting using the binomial theorem. Okay, so after we do this in our next class, we'll move on to locus, right? So this will be the end of using the Morse theorem. We'll move on to locus, equation of a circle. And finally, we'll end after doing this with the fundamental theorem of algebra, right? After we finish the fundamental theorem of algebra, this will bring us to the end of our first major section of our course in complex numbers. After that, we'll move on to coordinate geometry and then move from there. Okay.